Hello, everybody, and welcome to SciByte. Now, this show, if you haven't seen it already, which you shouldn't have unless you're like a time traveler or something, which I won't hold against you. It's just, This is our first episode ever. Just to give you kind of a rundown on what this is, you guys know Mars, Heather. She's been a guest star on our previous episodes of Jupiter at Night, and she was such a big hit with our audience and with us, just because she does all the work for us. So we gave her own show. So, again, my name is Jeremy.
And my name is Heather.
And tonight we're going to be talking about gravity. I know, heavy subject, right?
Oh, yeah. Had to have that joke in there.
I figured get it out of the way up front, just so nobody needs to be sitting around waiting for it to happen. Now, the reason we're talking about this is because NASA recently launched. Was it recently?
Well, it was launched. It shut down in December.
Oh, so it's already done with its work.
Yeah, it's done.
So we're kind of late to the game, but we're going to be talking about it anyway because it's fascinating. What they called it was the Gravity Probe B.
Probe B.
Mars, why don't you tell us a little bit about the probe itself, and maybe then we can get into what they were trying to discover up there by launching it.
Sure. We're looking at gravity and how it's affected by mass and space-time and how all these tie together. So, you had Sir Isaac Newton with the apple that didn't actually fall on his head. He just saw it fall from a tree.
What? Are you telling me they were lying to me?
No, it became a cartoon that it hit it on his head. But he just was walking through the park near campus and saw an apple fall.
And from that inspiration of watching gravity in work.
And lots of other things.
Yeah. And because he's a genius.
Well, that helps. It sometimes helps.
Now, Newton, inspired by the apple and his genius, discovered what they call, what did they call it? His universal gravitation theorem. Yeah. Which
Newtonian physics. It's the basics of a lot of different gravity calculations.
It's this thing right here. If you take a look, right there.
And it's saying that, the force of gravity has to do with the mass of the two objects, the distance from their centers, and lots of math, because math is awesome.
But to boil it down to kind of a layman's explanation, it's that every object in space pulls on another object.
Yeah, it says everything interacts.
Okay.
And the bigger the mass, the more it interacts. The farther away, the less it interacts.
Okay, well that makes sense, right? And it created an accurate model, more or less, of our solar system.
Yeah.
Of the orbits and everything.
Yeah, he was able to predict the existence of Neptune from watching the orbit of Uranus and able to see, it slows down here, it picks up here, it wobbles here. And from that, he was able to say, there's got to be something beyond it, about this size at about this distance, to make it act like that.
Wow, and all just using math. Now, that's all really cool, but it's wrong.
Well, it's not right for most things.
Well, now, you pointed out to me that we were able to use the Newtonian model of gravity to actually get to the moon and back. So it's not worthless. No,
it's pretty accurate for anything bigger than a molecule, anything less than the speed of light. It gets you pretty much all the way there. It's still a really accurate, really simple calculation.
But there is a better version of the gravitational model out there made by our good friend Albert Einstein.
Yep, general relativity and all that good stuff.
Now, this is where things start getting a little fuzzy because Albert uses the term space-time. Now, I'll be honest, that makes me cringe a little bit. But a lot of people have heard his analogy that instead of Newtonian gravity where it's just things pull on each other, Einstein's explanation, kind of, again, a layman's terminology, is that space-time is like a rubber sheet. Yeah. And the heavier an object is sitting on that rubber sheet, the more it pulls and warps it around itself. I've always found that fascinating, but a little hard to wrap my head around because space is not just three-dimensional. I mean, it's not two-dimensional, rather. It's not a sheet. It's more like almost like I like to think of it as a pudding or a Jell-O.
Jell-O.
With really big, heavy things in it that kind of mess stuff up right around it.
Instead of thinking of it like a trampoline, you're sitting in the middle.
Yeah,
your siblings put something on it, it just kind of rolls to you.
That's right. So
that was, it's not you and the ball interacting with each other. It's the fact that you're bending space and it's falling into the warped space. Mm-hmm. That's kind of what Einstein was saying.
And it turns out to be more accurate on more scales.
On the atomic scale and, speed of light. For that kind of stuff, then That's
you
kind
need
of
relativity and Einstein stuff.
Relativity and Einstein.
So correct me if I'm wrong, but that is what the gravity probe B was actually sent out into space to try and prove?
Yes. Yeah, it was sent out to prove and measure how much the Earth was warping the space around it.
Now, can you give me sort of a high-level explanation on how they plan to do that?
Sure. They send it on a polar orbit. Mm-hmm. So it's going around both the poles. Mm-hmm. And it uses a telescope and it points way out to a star. So you have this star way in the distance, so it'll stay aligned up on something. Then you have these gyroscopes. Now these kind of gyroscopes are not like the toy that, you spin the string up on and pull and it, it spins and it'll, stay on a string even sideways.
Mm-hmm. Although those are awesome.
Those are awesome. It's the same idea that it's something that's going to spin and wants to stay spinning in a certain direction. Mm-hmm. And so they put these in there, and then depending on how much it goes off, how much it moves, they can measure that by a magnetic field.
Okay, so they've got instruments trained on the gyroscopes. They're watching them spin while they're oriented at a distant star, which shouldn't be affected by the local Earth space-time distortions. So then, as this probe circles in a polar orbit, they were able to observe the fact that those gyroscopes fell off axis.
Yeah.
Right? They were pulled by the warping of space-time in Earth's immediate vicinity.
Yeah. They're able to see the pull and the spin. Even the rotation of the Earth was sort of like if you put, back to the rubber sheet, if you put a bowling ball on a rubber sheet and try to spin it, it's going to pull the rubber sheet along with it a little. So that's kind of like what Earth is doing to space-time. It pulls it along with it just a little.
That,
kind of creepy?
Kind of creepy. I mean, if you think about it, because that means that our planet is changing reality as we know it.
Yeah.
Now, the distortions that they were able to detect, first of all, you know what? Actually, before we get into the actual science of what they discovered, I want to talk a little bit about the tech that they used to build this gravity probe. Now, you were already talking about those, the gyroscopes. They're actually contained within spheres. I keep making gestures to things this size, but they're actually this size.
Yeah, they're ping-pong balls.
Ping-pong balls.
But they're perfectly spherical.
To within 40 atoms.
Yeah.
Which is not very much.
No, it's not. If you made it the size of the Earth, then the difference between the tallest mountain and the deepest canyon would be about 12 feet.
12 feet?
Yeah.
Well, that's pretty darn close. Close enough for science, right?
Yeah. I mean, Shatner's climbing a mountain would be a lot shorter.
So these ping pong balls, in order to get them so that they can spin freely in a free fall around a polar orbit, they had to contain them within frictionless materials, which I didn't even know that such a thing existed. I'll be straight up.
Yeah, not completely frictionless, but pretty darn close.
I get close enough for science, right?
Superfluids.
Superfluids.
These things are crazy. You put them in a bowl. You've seen, you put your water in a glass, or you put, from high school chemistry, you see the water kind of wicks up on the side of whatever container you have it in. But these superfluids don't just stop. They keep going all the way up the walls of whatever container you have it in, over the top, outside the container, until it's coated everything.
How do they do that?
It's a combination of all their properties. They've got specific electromagnetic properties.
The function of their molecules interacting with one another. In essence, is it that they tend to repel themselves, kind of?
Kind of.
At a certain level?
Yeah, it's just, there's a certain point where things...
Where they become magic.
Yeah, it becomes magic.
No, but because of the superfluid properties of this, they're using liquid helium, is it?
Yep, superfluid helium at about 2 Kelvin.
Which is really damn cold.
Yeah.
Negative 271 Celsius, negative 456 Fahrenheit.
Yeah.
That is amazingly cold. Because of the superfluid properties of this, as I mentioned earlier, this reduced friction to almost zero, so that these gyroscopes were able to spin freely.
Yeah, as long as you could keep pumping in the superfluid helium, there's very little friction, there's very little outside force acting on these things.
Okay, so that's the gyroscopes themselves, but how do you control the fact that the probe would be buffeted by solar winds or atmospheric distortions?
Solar winds, atmospheric. You have the whole thing sort of, it has a set of controls that go off one of them. It picked one of these gyroscopes. Mm-hmm. And anytime it started to see anything moving you know, from solar radiation or from atmosphere, because there's a little bit of atmosphere even way out there.
Mm-hmm.
It would, you know, some of this helium is obviously going to kind of boil off, so they had helium gas that they could put out to certain jets to kind of move it this way or move it that way to keep it perfectly aligned, perfectly balanced on this star. The way these worked is that these gyroscopes would create a magnetic field. So you didn't have to have actually anything looking at the gyroscope. You didn't have to have a marking on it.
Mm-hmm.
You could just measure the magnetic field, and it would align directly with its spin. So if it starts to go off, then the magnetic field would move, and you could measure that.
Which is actually how they ended up coming up with their final results, which was how much was Earth's gravity warping space-time in the local area. I find this fascinating because over the course of their mission, which did they end the mission because they ran out of helium? Because
that was part of it. It was it's one of these that it has a component. It's like taking food.
Mm-hmm.
Your food's only going to last so long.
Yeah, you can only bring so much helium.
Yeah, you're going to have a certain amount of helium that you bring. It's going to last, 11 months, or and that's how long it's going to be.
Mm-hmm.
So you just have to measure it, how long what it does in that time.
So now the results that they came up with by using their measurements, checking the rotation, the alteration of that gravitational field within these tiny little gyroscopes was, let me read what you wrote in our doc here because I find this amazing that we could even tell that this happened.
Yeah.
The pointer shifted by just 6,000 milliarc seconds. The width of a human hair as seen from 10 miles away.
Yep.
I can't see hairs 10 miles away. I'm sorry.
No.
My eyes don't work like that. I'm not Superman, despite the claims that have been all over the internet. So, but we had the instruments that were able to show us that over the course of that 11 months, it shifted. So space-time within our local neighborhood in the solar system shifted by that much, was dragged that much out of alignment by the Earth.
Yep. I mean, they could have measured even smaller than that. They could measure the width of one human hair from 20 miles away over the course of a year. If it took a year to move that much, they still could have measured that.
Why aren't we flying cars now? I just want to put that out there. Okay, so that is fascinating, and they came back, and it was a huge success. They found that what they wanted. They proved that space-time is a rubber sheet. Congratulations, science.
Space-time.
But now, you pointed out here that we already knew this, right?
Kind of.
I mean, the Apollo astronauts and their reflectors on the moon.
Yep. Because of those little reflective mirrors, we can see where the moon is to a position within millimeters. So if the moon moves just slightly differently, we can kind of calculate, wait a minute, that's doing something a little bit weird. It's just a little bit off. And it was, to some degree a lot higher precision. Mm-hmm. But in science, you like to come at things in different directions.
Well, sure. One time you land on the moon, another time you float something around the Earth. I see. Well, you want to have different ways to look at it.
Well, you want to measure things in different ways, too.
I think this is the first time we've mentioned this tonight, but that dragging of space-time that happens in the orbit, they call frame dragging.
Yep.
Which, as an editor of video podcasts, I run into that all the time.
Yep.
It's also boredom affects the space-time around it. I don't know if you've been able to tell that.
Yes. Think boredom has a gravity. Some sort of gravity molecule that we haven't been able to find yet.
It's probably another elemental quark, the boron.
Probably. Little gravitons are found in boredom.
Yeah. That's it. We just solved the universe's problems. Actually, I want to talk a little bit about the universe's problems because as we hinted at earlier, Einstein's model of gravity doesn't work at all scales. It breaks down at the speed of light. It breaks down on a quantum level, and it breaks down in the centers of black holes and stuff like that.
Yeah. Newtonian physics, all sorts of different physics. It doesn't really work everywhere.
So
Newtonian physics got Apollo 13 back to Earth.
Sure.
We're able to measure exactly
Newton.
Where they needed to go, how to come back to Earth, flip around the moon to come back.
But to be fair, the Earth and the moon, they're both kind of big. I mean, they're tough targets to miss if you're close enough.
You'd think.
But the idea that we're out there sending this gravity probe B out there to try to, I don't know if prove is the right word for it, but kind of verify that the model works.
Yeah.
When we already know that it doesn't in other circumstances. Has there been any like backlash over that, or
well, I mean,
how do particle physicists feel about the fact that we're pointing things at other stars when we could be studying quantum mechanics or something like that?
Oh, in science, there's always going to be that group that goes, no, you should have spent your money on my project, funding me.
Yes.
But, or, oh, of course that's silly. And then some people say, oh, of course that's obvious. And others would say, no, that's stupid. It can't be true.
Now,
scientists don't agree hardly on anything.
So there's no uniform model of gravity that works on these separate scales. Is there any model of gravity that works on a quantum scale at all?
Yeah.
But it's a completely different scale, right?
Yes. Yeah. I mean, the same physics that got us to the moon and back, if you apply it to atoms, it says the electrons will crash into the center of the atom. Yeah.
They can't really hold themselves in place.
Kind of appears that we're here.
Yeah. So we haven't flown off into space or collapsed into solid matter or anything like that.
So there had to be something different,
Mm-hmm.
So.
But now, if that's the case on this scale, and it's different in a different scale, I guess that's one of the greatest mysteries of our time in science, isn't it? Is how to kind of reconcile the two?
Yeah, it's like unifying all these different theories. And that's why a lot of scientists will say, hey, you know what? Even if we're pretty sure that we know there's this frame dragging because we have these mirrors on the moon, go send Gravity Probe B out. Let's check it out, because the more data, the merrier. And the better idea we have about any kind of scale of gravity. The more we find out about anything, the better the chance there is that some other genius is going to come along and say, wait a minute.
You remember that Gravity Probe B thing? It actually proved this.
It makes sense now. I mean, this one was in plans for decades.
Decades?
So, yeah.
Just to make some balls spin in space?
Yeah, well, they first came up with the idea it was like, hey, if we did this, and that was like back in 59, then we could measure it and it would prove or disprove it. And it just took till, in 2004. So it just took that long to be able for the science for us to be able to physically make the equipment needed to measure details enough and to sort of catch up and be able to do it. And get
it's almost like the tech was holding us back. We couldn't figure out the superfluids and gyroscopes.
The near perfect ones.
Oh, right. Sorry. Near perfect. That's the important part.
Yeah. Well, I mean, if you're trying to measure something, 1 inch across, and you have a camera that can give you, an estimate of, oh, it's 6 inches plus or minus 10.
Right.
You're not really going to measure 1 inch all that well.
That is not close enough for science.
No, that's not close enough for science.
Now, I want to circle back to something that we touched on earlier, because I want to tease this for our next round of what SciByte is going to be talking about.
Okay.
We started talking about space-time.
Yes.
Now, as I said earlier, the concept of space and time being the same thing on some levels kind of makes me a little nervous and feel like I don't know what the universe is made of. But because I had to do so much research on this topic in order to be able to keep up with you while you talk about gravity and Newton and Einstein and all that stuff, I actually started to learn a little. As my high school astronomy teacher used to say, I was folding my brain. I've decided to take it upon myself to pitch our next episode as being all about time. So we will start by trying to explain space-time. God help us. And then we will get into a conceptual conversation of how time works as far as we can manage to understand it, and and more and other stuff, and it'll be fascinating. I'm already way into the concept.
Oh yeah.
So is there anything else that you would like to touch on before we go ahead and let people go and give their brains a break after today's SciByte?
Dark matter.
Mm-hmm.
That was something I wanted to bring up.
Dark matter?
Yes.
This is another area where current gravitational models kind of break down, because by current gravitational models, as I understand it, galaxies shouldn't stay together.
Yeah.
They should spin off into space.
There's this, this theory that, we can see, a certain amount of the universe, but math says that this much more gravity, this much more mass has to be there.
Well, I read somewhere, and this could be completely off base, but I read somewhere that they estimate like 96% of the universe's mass cannot be detected.
Yep.
By current means.
The mass and the energy.
Yeah.
That we're only seeing a little less than 5%.
That's
of what the
not
universe
much.
is.
That is not close enough for science.
No.
And that's our new tagline.
Close enough or not close enough for science.
Right. So have they been talking about dark matter? Have they been trying to figure out ways to actually either prove its existence or...
Well, yeah, they can kind of, to some degree, prove that there's something else there. I mean, there's, you can look at black holes and you can see how fast things are rotating around them, or you can see galaxies and see how fast things are rotating. And just by the math, you can say there must be this much mass there. Therefore, something's missing.
And that comes up as dark energy or dark matter.
Yeah.
That, again, that's just something that starts to break my brain a little bit when we have this concept of something that we can detect is there, but we can't detect that it's there. It's
not directly. You see
it's
the
like
results of it?
the math works,
yeah,
but the observation doesn't. So maybe we'll do another episode in the future on the more of the fine-tuning theories of dark matter and dark energy. But for now, that's all the time we have for this week's episode of SciByte. We'll be back next week to discuss the fine-tuning mechanics of time itself. If you don't catch us next week, it's probably because we figured so much out about it that we just made a DeLorean and traveled to wherever we wanted to.
Yeah.
And you're out of luck. All right, we'll catch you guys later.